All right, it looks like a homework assignment snuck in there from last semester. Let's take a look at it. Oh. So homework assignment 1, create a program that will print your name. Use the escape sequence \quote to print your favorite quote or saying or song lyric. Well, that doesn't give you a very good example. And then use the escape sequence // to print the following output. I'm almost not liking number 2. I certainly like number 3. I may edit the document to take part 2 out. If you've already done part 2, that's fine. To do part 2, it would just look like this, something like this. Printf, parentheses, quote, I don't know. My favorite word is %, quote, you know, weasel. Is that how you spell weasel? I don't know, so I'm going to spell puppy. There, that's my favorite word. And then %, quote, and then quote, and then a new line. Right there should be a new line. Right? Am I in the right place? No, right there. Okay, that's what it should look like. Except for some reason I said favorite quote. That would be, you know, it could be several lines long. But when this ran, this would get translated into a quote. And this would get translated into a quote. So my favorite word is puppy. That's how you would do part 2. If you already did part 2, great. But I feel like getting rid of it. Sorry. And we're going to modify the due date on that one to make it due a week from today, since I don't think we talked about this homework. It's not ringing a bell to me. Okay, so and we just save it to print a message that looks like this. What could we put quotes around? My favorite book is Harry Potter and the Scarf of yarn of wool. Okay. Substitute your own favorite book. All right. I like that better. That was a little bit too vague. And then use the escape sequence // to print the following. So the trick there is if you put a / in your print statement, it's just going to go to the new line.
Right.
And if you put /t, it's going to go to a tab. So you're going to have to do %/, if I correctly recall. We better try that out. Let's load Visual Studio up, make sure that we know what we're doing. Oh, by the way, I found what I was looking for in the boilerplate last time, and I think I've uploaded a new copy of the boilerplate that I want us to use.
Okay.
Is it in modules? Let's take a look. Let's take a look. Okay, fine. Don't be in my boilerplate. Still not there. No, that's the C++ one. All right. Here's what our new boilerplate will look like. This is the only mystery one. We may not need that one for a while. We only need that one if we are compiling from the command prompt and we are not using Visual Studio or Xcode or anything like that. So we could probably leave that one out. However, I will upload this boilerplate so you can just download it and use it whenever you want. Why don't we just stick that right up at the very top in syllabus and class information to make it easy to find. So that's a boilerplate I'm going to be using from now on. All right, hopefully homework 1 now makes sense. Now let's go look at homework assignment 2. I think homework assignment 2 should be good to go. But I still want to link to the correct file. Yeah, I'm going to get rid of that. People know where to look now. They go and look in the modules, they'll find homework. Conversions using modulus. Yeah, we went over that pretty well. Yeah. Okay, so let's go and modify the due date for the assignment. Assignment 1. It's going to be due after assignment 2, but that's okay. We're good with that. We can figure that out. Okay. We finished PowerPoint 1, I believe. Let's take a look and make sure that that's absolutely true. Yes, we did. Let's take a look at chapter 2. All right. So, the 4 parts of a variable. I think I've mentioned this. The name, the type, the value, and the address. Every variable has a name, every variable has a type, every variable has an address. Usually we only care about the first 3 things. The program knows what the address is, but we don't know unless we have the program printed out. The address is just, some random byte out of the gigabytes of memory that we have on our computer. So if we have something like this, int x equals 3, the name is x, the type is int, the value is 3, and the address, yeah, well, the computer could tell us. We don't know it off. We don't know just by looking at that. And if we do something else, double space y, its name is y, its type is double, its value, we don't know its value. we're going to say that it's unassigned. It hasn't been given a value yet. There may really be a number stored in it, but it's going to be a random number, just whatever happened to be in memory at that point. We never want to use an unassigned variable. So until we copy something into it, its value is unassigned. We still don't know the address. We can print it out, but we don't know. Let's take a look at what memory addresses look like. So let's go ahead and create a new project. Empty project. C underscore lecture underscore D. All right, our new boilerplate. Did I upload it? Yes, I did. So under modules, the very top thing is a boilerplate. We're going to go ahead and use this new boilerplate. We'll talk about the things that we just added to it. Can I just copy out of here? That'd be neat if I could copy out of here. Woohoo! All right. Yeah. So I need to add a new file. So I need my Solution Explorer. If yours isn't up, I need to right-click and insert on source files. And of course, your Mac users should be doing something a little bit different. New item. Lecture C.C. Wait, it's lecture D. Delete that or rename it. Rename lecture D. All right. And then paste that stuff that I copied. Hope that it looks good. Did that work? Well, that looks kind of lame. We could get it to work. We could just go and hit all of these, but I'd rather it work perfectly. We'll have to work on getting that to work. We might have to download the file and open it. Okay, so standard IO is for the printf command. And that's why we have that. Standard live is for the system command. Now, it seemed like half the time system was working great without doing that. But then suddenly we had computers where system was not working. So we add that. And a math.h is just so that we get the POW command, the power of, like if we want to calculate 3 to the power of 4, we're going to need that. And then lastly, this weird looking one, pragma warning, we're not going to even need that until we start compiling under a Linux, a Unix kind of environment, compiling by hand. So the Mac users and the Windows users aren't going to see any effect from that. We don't really care about it, but I put it in there anyway so that when we do need it, I know where it is. Okay, so let's declare two variables. Int x equals 3, double y. Let's see if we can print out their values. Printf, parentheses, quote, x equals %d, address equals %p, \n, end quote. And we're going to fill in those placeholders. So comma x, comma, and we need the address of x. So we're going to use the ampersand symbol to mean address. Then we're going to do the same thing for y. We want to print out y. Now y doesn't have a value. I'm halfway expecting, I hope to at least see a warning. And if it gives us an error message for this, so much the better. Printf y equals %f. Ooh, why did I change that? This was a %d. Well, %d is for integers and whole numbers like longs and unsigned shorts and everything. Unsigned short sounds like something you'd get from a, at the athletic store. Anyways, %f is for floating points like floats and doubles. So y equals %f, address equals %p, \n, and we still need our two values to fill in the two placeholders. So after the end quote, comma, y, comma, ampersand y, address of y. Now let's see if it fails because we're using an uninitialized variable or if it works. It worked, but check this out. Look at that nasty value. That's even worse than I was expecting. All right, so if you use an uninitialized variable, it's probably not going to be a good result. But if we look, we see the memory addresses up here. Of course, a print is tiny, so seeing is kind of a optimistic view, but here we go. Really? No, scroll left and right. Okay, that's its memory address. And notice it's even in some funky weird letters. I mean, you know, letters and numbers. This is called hexadecimal. We don't really care what that means right now. We just know that it's a memory address, and we really don't know it unless we ask the compiler. So I'll never ask you a quiz question. What is a memory address for Y? Because we wouldn't know. We'd have to type up a program and run it, and it would differ every time we ran it or on every different machine. Lots of different types. Lots of different types of variables. These should be lowercase. That should be a lowercase c, and a lowercase I, and a lowercase f, and a lowercase d, and a lowercase v. They got most of these right. They didn't get that. Ooh, and they misspelled that long singed int. It's singed. It's been burned. You'd have to swap the G in the end to make it unsigned. Okay, so what is a signed versus an unsigned? A signed means that it supports negative values. Unsigned means that it can be positive only. Why would you want a positive only number? Because it lets you store larger values in it. And a short int is a small int. We'll talk about what small means. That can hold a value from negative 32,000 to positive 32,000. And you're hardly ever going to use a short int. So don't stress it. An unsigned int, since it can't go negative, is just 0, but it can go twice as large. So you can hold a bigger number in it. Now, is this the only kind of unsigned variable there is? No, there are signed and there are unsigned ints as well as short ints. I don't know why they listed it like this. We're going to kind of revise this, but here's something to notice, the size of it. The number of bytes. There's 8 bits in a byte. Copy that and paste that into the notes for future benefit of future civilizations. There we go. That's our boilerplate. Each byte is 8 bits. Well, what's a bit? It's a 0 or 1. So a byte can have the values 0, 0, 0, 0, 0, 0, 0, 0, all the way out to 1, 1, 1, 1, 1, 1, 1, 1, 1. Now, what does that mean? We don't really know yet. I don't think we've talked about it, but it means that the lowest value can be a 0, and the highest value can be a 255. So there are 256 different possible values that can be stored in a single byte. Now, that's not a very big number, so you use 2 bytes to hold bigger numbers, or 4 bytes to hold even bigger numbers, or 8 bytes to hold huge numbers. So we have 1 byte values, which are called chars. Why chars? Because they hold a single letter of information. We don't have more than 255 letters, so that'll work. 2 bytes is called a short int, or just a short. Just that word works as well. 4 bytes is a regular int. 8 bytes should be a long int, or just a long. Now in Microsoft C, though, a long is just the same size as an int. And if you really want to get a long int, you have to use the word longlong, which is ludicrous. So we could declare variables of each type, right? Here's a character called ch. Here's a short called s. Here's an int called I. And here's a long int, long, called L. That's not a 1, that's an L. And a long called LL. And that's an LL and not an 11. And we're going to print out the size of each one of those. So we're going to have like 5 print statements. We'll probably copy and paste some stuff in order to get that to work. We have a function called sizeOf, which tells us how many bytes each one of these uses. Printf, parentheses, quote, ch size is %d \n, comma, size of parentheses ch in parentheses semicolon. I just copy that, paste it 4 more times. If you don't know how I'm copying so fast, I'm moving my cursor to the beginning of the line and I'm holding the shift button and the down cursor. And that selects a line. Saves me from having to grab the mouse. I'm going to paste that so that I can then just change that to an S and an I and an L and an LL. Same thing, I got to change these as well. That's an S. That's an I. This is an L and an LL. All right, so what we're seeing is that in Microsoft Windows Visual Studio, a long is the same size as an int. If you run this on your Mac or on a Linux compiler, it's going to tell you that a long is an A. Well, we can't do anything about it. But what that means for us is that if we want to hold a big number, we're going to use a long. The absolute value, the largest value that these things can support, we can see those by looking at this PowerPoint. The longest of a character, the range is 0 to 255. If we need a value larger than those, we're not going to use a char. Normally, you're not going to use a char to hold a number anyways. A short int, the largest value is about 32,000. 65,000 if you use an unsigned. The largest int, that's wrong. Bang my head against it. This entire page needs to be deleted. The largest int is 2 billion. The largest longlong, man, this is so wrong. I can't believe they got this so wrong. Dadgum. We're going to have to fix that. We're going to have to go and get the right values and put it into our notes because that is completely wrong. All right, now we can see that there's a great million different types of data. If we screenshotted that and pasted it into the PowerPoint and re-uploaded it, we'd be happier campers. So let me try to do that. Good enough. All right. So the largest of an int is supposed to be 2 billion. The largest of an unsigned int is actually 4 billion. I don't know why. Dadgum, even this page is wrong. Whatever. And then the largest of a long is really large. 9 super quadzillion, billion, trillion, whatever, right? Large number. That's even bigger than the national debt. There's probably not many numbers we're going to put in there that needs to be larger than that. Ints are whole numbers. All of these are for whole numbers only. If we need to store decimals, they take a different kind of data. The number of bytes dictates how wide, how big the number can be. So that's why an int can hold more than a short, because a short is only 2 bytes and an int is 4 bytes. I'm not going to ask you to know these exact numbers. Good thing, because they're wrong on every page we look at. But I do want you to know that a long holds much larger values than an int. which holds larger values than a short, which holds larger values than a char. So let's put that as a hierarchy. I'm going to put long here. Really silly sounding, but we can't do anything about it. Okay, longs, largest value is about 9 super zillion billion gajillion. All right, and int's largest value is about 2 billion. A short's largest value is about 32,000. And a char's unsigned value, char's largest value, sorry, not unsigned, is exactly 255. There are unsigned versions. There are signed and unsigned. Signed is the default. If you don't put any more words on there, it's signed. So no special keyword needed. Unsigned, you use the unsigned keyword. Like unsigned short, unsigned int, unsigned long. And if you want to, you can put the word int after these as well, but they're kind of implied. So you don't have to put the word int there or there. What does that give you? It gives you a number that can only be positive, that cannot be negative, and can hold a value twice as large as the signed version of it. Now the reason for that, not that I wanted to get into the binary lecture, and since so many students are absent today, I really don't want to, is that if you had well, I guess we're going to do a binary lecture just a little bit. Say we're in a car with an odometer, and the odometer's got 4 numbers on it, right? And we know that if we're cruising along, we go past a mile marker, we go past another mile marker, we go past another mile marker. Eventually, right, we're going to get to that point. Now this is decimal. Decimal means base 10. Sorry for all the math terms. Base 10 means that it's got 10 digits in the counting system. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are our 10 digits. When a column maxes out, it can't get any larger. So when a column maxes out, and we know this we know this intuitively because we've learned it since grade school, that turns back to a 0. It goes from the largest to the smallest value, and then the next one gets incremented by 1. Right? So it can keep counting at that point. And when you get to 99, right, again, we know what happens. It's maxed out, it's at its largest value, so it's got to go to 0. So we add 1 to the next column. Well, it can't get any larger either. So it turns into a 0, and the next one gets incremented. Like that. Right? So that's our odometer for base 10, made out of, 10 digits. There's 10 different digits in this system. We have 10 fingers, 10 digits. We're all good. Okay, so that's decimal. The largest value that can be held in 4 digits is 9,999. Now that's because our odometers never go negative. We can't slam our car into reverse and get a negative mileage reading. Be kind of nice, but drive 100 miles backwards, get more money for your car. Can't do that. So if we had to support negative numbers, we would need an additional bit of information. And I actually use the term bit on purpose because, bits. But we need something to indicate whether it's a minus or a positive number. And, we know, in our counting system, we put a dash in front of it. So that's our decimal car. That's our base 10 odometer. If we ever got to 9999 and we drove another mile, I don't know if y'all have ever had a car that could do this, but it would roll over, right? It would turn back into all zeros. Now, I did have a car that rolled over. No, it never rolled over because it would have rolled over 999,999 and it fell apart long before then. Anyways, so this is called overflow. Overflow is when you exceed the amount of space. So it rolls over. All right. So let's get into our binary odometer. Binary meaning 2. There's only 2 digits in binary. On and off. So we hop in our car. We drive a mile. Now we drive another mile. We can't go 2, right? Because our highest digit is a 1. So what are we going to do? What happens when you hit your highest digit? It goes to 0, and we add 1 to the next column. That looks weird. Looks like 10. Alrighty, and now we're going to go another mile. Alright, now let's go another mile. Whoops, same problem. What does this really become? Instead of being a 2, that 1 changes back to a what? A 0, and we add a 1 to that one. Whoops, can't add 1 to that one, so that one also becomes a 0. And there we go. Now we've almost maxed it out. If we only had 3 bits, then we would have maxed it out and we would have rollover. But not yet. When we drive 1 more mile, that becomes a 0, that becomes a 0, that becomes a 0, and that one becomes a 1. And then it kind of just repeats. Let's see if I can make a mistake here. So that is 16 different values, starting from here down. Hope I get this right because I don't want to go back and correct them. Okay, by miracle I got it right. So after we've driven 15 miles in our car, in decimal, our binary car's odometer is going to show 1111. And if we drive 1 more mile, those are all going to flip back to being 0. And we're going to have data corruption. We're going to have overflow. It rolled back to 0. Again, these are only positive numbers. Now, this is only 4 bits. If we had 8 bits, if we were going from 0000, 0000, all the way to 1111, 1111, that would be possible value from 0 up to 255. That's the range for a care. Again, those are all positive numbers. What if we needed to support negative numbers? What we could say is that the first bit indicates whether it's positive or negative. So if we had an assigned version of an 8-bit number, the first bit, if set, means it's a negative number. So we could count all the way from 00. I'm going to put a space there because my brain starts to twist. We could go from that far to that far. That would be the largest number we could count with a signed 8-bit number. Because as soon as it rolls over and that one shows up there, it's going to be counted as a negative number. So this is a 0 up to 127. And the rest of them, if they start with a 1 or whatever, these are all negative numbers. And there's 128 negative numbers, I believe, or negative 127 more negative numbers, something like that. By the way, these are stored in something called 2's complement, which we don't really care about. We're not going to talk about what that means. It's not exactly as easy as just saying that, oh, because that's a 1, then the number is negative, because what would all zeros be? That would be 0, and then, oh, it's -0. That doesn't make sense. So instead, this is a -1. But we're not going to really care about that. We're just going to notice that we have fewer bits of information dedicated to the real value of it, because one of them had to be used up for the sign, right? So if we have unsigned 8 bits, we can count up to 255, 0 to 255. If we have signed 8 bits, we can go I really think that's -128. I can't prove it, but I think that is right. We can go from +127 to -128 to +127. It's just like shifting the range, right? You know, if you could only have positive temperatures from 1 to 100, but then if you shifted everything down 50 degrees to allow you to have negative numbers, then it'd be +50 to -50. So the signed bit uses up some of your information. So why do we talk about that? To understand why unsigned ints can support larger values. So the largest value for an unsigned int is about 65,000. Oh wait, that's the largest value for a short, 65,000. The largest value for an int is about 4 billion. And the largest value for a longlong is 2 times whatever that was. Right. Even more super gazillion, billion, whatever. Okay, so now we've learned how to count in binary. Well, how did I know that a 1111 was equal to a 15? Well, because I've taught the class before. No, there's another reason as well. If we have base 10 numbers, like if we have the number 1,234 in base 10, these are really places. And if we think back to grade school or junior high, we talked about the ones place, the tens place, the hundreds place, and the thousands place. So this is 4 in the ones place. This is 3 in the tens place. This is 2 in the hundreds place. And this is 1 in the thousands place. And if we added those all up together, that's a 4, that's a 30, that's a 200, and we don't normally think about numbers like this, but that's just because it's built in. We've learned this for so long, you know, that we understand it instinctively. And so if we added all those numbers together, we get 1,234. Now presto, we went from base 10 to base 10. That was not a real accomplishment. But what this means is that this one is 10 to the power of 0. 10 to the power of 0 is 1. Anything to the power of 0 is 1. Sorry to get so mathy, but 10 to the power of 0 is 1, which is why this is a ones place. 10 to the power of 1 is just 10. So that's why this is the tens place. 10 to the power of 2 is 10 times 10. So that's 100. And 10 to the power of 3 is what? 1,000. So yeah, you can kind of think of it as that power of just being how many zeros there are, right? 1 0, 2 zeros, 3 zeros. No zeros. That's what it means when we have these place values in base 10, in decimal. What if we have binary? Base 2. Well, this is 2. Let's put some spaces out here. This is 2 to the power of 0. That's still not going to be large enough to hold what I'm trying to do. This is going to be 2 to the power of 1. This is going to be 2 to the power of 2. And 2 to the power of 3. So 2 to the power of 0, anything to the power of 0 is 1. 2 to the power of 1 is just itself. What's 2 squared? 4. What's 2 cubed? 8. So these are different place values. So if we had the number 1010, This is an 8, or a 1 times an 8. That's the 8th place. We could count backwards, but I like going left to right now. Plus nothing times 4. That's the 4th place. Plus 1 times the 2's place. And how many do we have in the 1's place? Right there. That's the 1's place. So how many we got? None. So 0 times 1. And so if we add an 8 plus a 2, that totals up a 10. Decimal 10. So if we have 1, 1, 1, 1, they're all lit up. That's the same as an 8's place plus a 4's place plus a 2's place plus a 1. So that's an 8 plus a 4 plus a 2 plus a 1 equals a 15. If we have 8 bits, the powers of 2 keep going. 1, 2, 4, 8, 16, 32, 64, 128. So 128, 64, 32, 16, 8, 4, 2, 1. If we have all 1s all the way across, then that's a 128 plus a 64. Which is equal to, I'm not going to whip out the calculator, I just happen to have this one memorized, is equal to 255. And so you see why the more bits you have, the larger number, right? Because if we had an extra 8 bits, we could add a 256 and a 512 and a 1024 and however, you know, I don't know the largest number. But that's why 8 bits can hold a number up to 255, while 4 bits can hold a number of up to 15. 8 bits is about the minimum that computers address anymore. RAM, memory, is addressed in bytes. Byte is 8 bits. So pretty much computers address memory in bytes, 8 bits, so each byte can hold one number between 0 and 255. But a 4-byte number can hold a number of up to 2 billion, because that would be 32 bits. I'm not going to show us adding together 32 bits, but it'd be a lot of them, right? And then the long is 64 bits, and so if we had 64 ones in a row and we kept going up by powers of 2, it'd be a really big number. Okay, we've talked about bits just about long enough, I think. Except I want you to show me what 1101 in binary is in decimal. Are there any 8s in it? Which placeholder is the place? We could work backwards. Are there any 1s in it? This is the 1's place, so there is a 1. Are there any 2s in it? No. Are there any 4s in it?
No.
Yep, there's a 4. 1's place, 2's place, 4's place, and then are there any 8s in it?
Yes.
Yep, so this is an 8 plus a 4 plus a no 2's, there's no 2's, plus a 1, and so that's equal to 13. And if we went back and confirmed, we had all these written out like that, they all add up correctly. Like 0111, there's no 8's, but there's a 4, there's a 2, plus a 1, and that adds up to 7. And we're not going to be concentrating on this each and every day, so if your eyes rolled up a little bit at this, that's okay. I just want you to have the idea. Right. Just want you to have the idea that more bits means the more bytes, the larger the value that can be stored in that particular slot. And if you have to have a signed bit to support a negative number, it means that the number cannot go as large, but it can go negative. So, advice. Don't bother using shorts unless you have, that really sounds weird. Don't bother using short integers unless you really have a reason to. So use ints as a matter of course, unless the number needs to be larger than 2 billion. If that's the case, otherwise, use a longlong. Since it can go up to, 9 gazillion billion. There's no reason to mess with trying to store numbers in chars or unsigned shorts. I wouldn't bother using unsigned numbers at all. You might think to yourself, well, the age, nobody gets to be older than 100, or, so I could use an unsigned short to hold. Don't bother. That's thinking too hard about it. Just stick it in an int and you're good to go. Now, looking back at this PowerPoint here. Guess I'm going to have to make my own chart. Okay, here's this fancy term, literal. What is a literal? More fancy terms that I've seen only in this book, not others. Let's go talk about what a literal is. A literal is something that is, quote, literally typed into the program. When I say, if I went down here and I said int age equals 20. Yeah, that was a long time ago for me. 20 is a so-called literal. It's literally typed into the program. There's no way I could change it without opening the program and editing it with an editor, right? It's not something the user typed in. It's just burned into the program. One fancy word for it, not fancy word, but a colloquial term for it is it's hard-coded into the program, right? Nowhere is the user being asked for their age. It's just being assigned 20, and that's too bad. Unless you have access to the source code, you're not going to be able to change it. So 20 is what's known as a literal. It's also known as a constant, right? Because it can't change. If you tried to do, 20 plus, well, anyways, it's the number 20. It always means 20. The textbook is going to tell us that this is what's known as a primary constant. No, it's not. I'll give it a different name. This is an unnamed constant. It doesn't have a name. Yeah, it looks like it does too have a name. It's called age. No, the number 20 is just the number 20. It doesn't have a name. It's stored in a variable called age. But that's just a copy of the data, right? Just like if you have the Declaration of Independence, you have the original one. That's just hopefully a constant. Hopefully nobody's going to be writing on it, changing the Constitution or the original Declaration. So a copy of 20 gets put into age. What if you want a named constant? What if you want to be able to refer to a value over and over and over? You can do this. Const int max underscore age is equal to 199. Anybody older than 199 years old doesn't get any more Social Security. They've lived too long. So that's our maximum age for whatever purpose. Or what if we need a tax rate? Well, a tax is a floating point number, not an integer, because got to like be 8.25% or something like that. So instead of storing it into an int, I'm going to store it into a floating point data value. I'm going to pick the word double, and we will talk about what a double is later. Just accept that it's not an integer, it's not a whole number. Const double pi is equal to 3.14159. Now, it's not really equal to that, right? Pi goes on infinitely, but I'm not going to type in an infinite number of digits. So now, then whenever we need to do some math, like double area is equal to 2 times pi times the radius, 2 times pi times the radius, well, that's ignoring the fact that we don't have a value for radius yet. But let's say that we pick one, and radius is equal to 3. So that means that anytime we want to use the value for pi, we can just use that word. But it's a constant. It can't change unless we edit the program. Again, unless we edit the program because the value of a literal got copied into it. So if we try to change the value of pi, if we pass a law saying that pi is 4, no, it didn't work. We are prevented. The programmer, us, are prevented from changing that value. The compiler will not allow it to compile because it has been marked as a constant and already given a different value. So that's a named constant. So pi is a named constant. It's a value that has a name. Now, why do you use constants at all? Because what if I do know the value of pi after 16 digits? Google that up, right? Pi to 16 digits. I could copy and paste that. Oh boy, out to 10,000 digits. All right, so anyways, right. I'm going to undo this because I'm not expecting y'all to type it, but I could do that. And then I could use these letters to represent pi without having to type that in over and over and over again into my code and probably get it wrong, right? I mean, there's very low likelihood that I'd be able to type that 10 times in a row and get it right each time, unless I was copying and pasting. And what if I copied it from the wrong source? What if I didn't check and it should have been rounded up to 3.3? Now, anyways, if we just put it in one place, then if it ever needs to be changed, we only have to change it in one place, even if I use that variable, 100 times in my code. So we avoid, when possible, hard coding values. Hard coding values are values that should not ever change, like pi. I should instead declare a constant named pi and use it. I'm going to go back to leaving this as 3.141.9 because that's usually what I have people type because it's not too hard to type. A number like 3.14159, or there's another one, double x is equal to 4 times 6.022e23. Unless you're a chemistry or physics major, you don't know what that number is. You have no idea what that number is. It's called Avogadro's number. Well, I don't even know what Avogadro's number is. But if somewhere I had that defined as a constant, then when I did this, and I used that over and over and over, you'd at least have a clue that you could go and Google that to find out what it really meant. Otherwise, you don't, right? So, otherwise, it's a magic number. We have no idea what it is, and I might type it wrong if I'm using it in multiple places. What about that? That's a magic number too. Well, it's part of a formula. 2 pi r, or pi r squared. Oh, by the way, that's the wrong formula. I just noticed this is diameter, the formula for diameter. So, magic numbers you want to avoid, but if it's just part of a formula, like if the formula is 2 over 3 times something, you don't need to declare one constant for 2 and another constant for 3 and stuff like that. But if it's some oddball looking number, I'd go ahead and declare it as a constant. You can even declare your constants outside of your code. I could cut these and paste them above my main. Why would I do that? Because if I have more than one function in this C file, they could all use those constants. Whereas if they're defined as just being part of main, then the other functions that I declare would not be able to use them. So I could put a comment up here to say that these are constants. Notice I made these uppercase letters. I usually don't use uppercase letters, or certainly don't make the entire thing uppercase in my variables, but for constants, that's the agreed upon standard. Just about all programs make their constants uppercase letters. And if you took fundamentals of programming with Donna Wilson or I or somebody, then even though the Python programming language doesn't actually have constants, we kind of agree, because the book said so, that if you make something uppercase, you treat it like it's a constant. And then it can serve the same purpose, right? It just, the compiler won't catch it if you try to reset pi to something else. But we can treat it like it's a constant. All right, this is getting all a little bit abstract. We have not learned much that's real programming, except we've learned that there's different kind of data types, that they can be signed or unsigned. The size of them doesn't differ. If I make this an unsigned longlong, it's still going to be 8 bytes. It's not going to change what it printed here. So these are integer types. I'm going to make a comment to the effect that these are integer types. There are also floating point types because integers are for whole numbers only. So let's put some floating point types in there. Underneath all those printf statements, I'm going to put some floating point types. They support decimal points. There's only 2. There's float and double. A float is 4 bytes. And I forget the largest value for a float. If we look it up here, we'll probably find it. Or not. Well, we can Google it up. Maximum C float. Oh yeah, you're not going to tell me. I'm just going to make it up. A float is 4 bytes. A double is 8 bytes, so it can hold much larger number. Don't ask me why sometimes I write the word out and sometimes I spell the English version. 4 bytes can hold up to, or I should say float, really, I should have been able to find that. It should have come right up. Maximum 4 byte float value. Here we go. Up to times 10 to the 38. Right, a 1 followed by 38 zeros. You would not want to get larger than that with a float. A double, since it's 8 bytes, can hold much larger values. Can hold up to 10 to the 340 or something like that. Huge number, right? 1 followed by 340 zeros. Okay, excuse me, 308. Got it wrong. Still a huge number. Use double, just as a matter of course. Just like I said, always use int, use double. But they use twice as much memory. Yeah, but it's important to use doubles because they're way more accurate. What do you mean accurate? Isn't a number a number? Well, if you only have a certain number of bytes, you only have a certain amount of space to hold the 2 parts of a floating point number. What do I mean by that? Let's pretend that you only had 4 digits in which to write a floating point number. A floating point number has 2 parts, right? 3.1 times 10 to the 8. It's got this part, and it's got this part. So if we only had 4 digits to store our value, we might be able to store the 3 and the 1 there, and the 0 and the 8 there, something like that. The largest value we'd be able to store would be 99, which would be 9.9 to the power of 10 to the 99. Again, too much math. But we see here that this is just kind of an approximation. Back when we had an integer, we at least had 4 places for our digits. Now we only have 2 places for our digits. You know, we have a very low resolution, right? It's only got, you know, into 0.1, 0.2, 0.3, 0.4. It can't be 0.111, 0.222. Now, we don't only have 4 bits for our floats. We've got 32, so they're a lot more precise than that. But still, you can get into what are known as floating point errors or rounding errors. Let's see if we can get one to come up, and this will be the last thing we do today, is we're going to start adding the number 0.1 to a floating point number, printing it out each time, and seeing if we ever get a floating point value, floating point error. So I'm going to just declare a float called f, and I'm going to set it equal to 0.0. Then I'm going to start adding 1 to it. I'm going to add 1 to it 10 times. That word plus plus, so symbols plus plus, is the same as writing f equals f plus 1. They mean the same thing. So f plus plus is the same as writing f equals f plus 1. It's just a lot shorter. But I want to do that 10 times. So twice, 3 times, 4 times. This is getting tedious. I might do a little bit of cutting and pasting. 6 times, 8 times, 10 times. That's not what I wanted to do. Dadgummit. Erase all that. I don't want to add 1 to it. I want to add 0.1 to it each time, because that's what triggers the floating point error. F plus equals 0.1. Now maybe you saw that syntax in Python. It means F equals F plus 0.1. And then just copy and paste that 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now what should that number equal? By the time you add 0.1 to something 10 times, that's like 10 dimes. What should the value equal? You've added 0.1 to itself 10 times. It's like having 10 dimes. 10 times 0.1 is what?
100.
1. Exactly 1. Right, 100 cents, 100%, it's equal to 1. So let's print out f minus 1. Print f, parentheses, quote, f minus 1 equals %f backslash n. I had to use %f because it's a floating point type. If it was an integer, if it was an int or a long or something, I'd put d there. So %f comma f minus 1. And it's not going to be 0 like it should be. Oh, by the way, my program is still running, so I don't have the continue button active there. I mean, I don't have the debug button active. I can stop the program just by clicking that red square that stops it, or I can find the program where it's running and close it, and it'll be ready to go then. Woohoo! Truncation from float. Are these errors? One error. Where's my error? Okay. Be that way. Be a brat. Add an F to each one of these lines like this. If you're assigning a float, you have to put an F after your number. I forgot that. X redefinition, different types. All right. Where did I do that? Aha. Just delete that line. Comment it out, something. Get rid of it as fast as possible if you've typed it. If you have that error, X redefined, just comment it out. We don't care. And what do you know? It didn't show the rounding error. Maybe we can tease the rounding error out by telling it how many decimal places to print here. I want it to show 16 decimal places. So to get 16 decimal places, I'm going to use a special syntax on that placeholder. %.16f. The decimal point means there's going to be a decimal point involved, and the 16 means that we support 16 digits after the decimal point. And there we go, right? We wanted it to say 0. it shows something else other than 0. That's a rounding. That's a rounding error. It's a floating point error. That's a pretty small number, right? The difference is pretty small, but it's very there, right? So when you're using floating point numbers, you have to do some little bit of care to make sure that that won't throw you off. If I'd had an if statement, if I'd had if f equals 0, it wouldn't have worked because it didn't equal 0. It equaled something a little bit more or a little bit less. And you have to take that into account. And we're not going to talk about how to take that into account. I just wanted to show you that the above shows floating point rounding error. F does not equal exactly 0. Now why is that? Computers are supposed to be precise. They're supposed to be perfect. Well, no numbering system is perfect, right? We use base 10. We use decimal. It's not perfect. What do I mean by that? What if you divide 1 by 3? What does that equal to? It's equal to that? No. If we type in 1 divided by 3 on our calculator, it's going to show something like that. But even that's not right. Right? It's an infinitely repeating number. Okay, I'm going to delete that. But you get the idea. Base 10 cannot accurately display the value 1 divided by 3, no matter how many digits of storage you allocated to it. It cannot be perfectly accurate. So if we were trying to add things together and they wound up being, multiples of 3, or 1 over 3 or 1 over 6 or something like that, then it would not be precise. It would be an infinitely repeating number. And yeah, in math classes, maybe you put a vertical bar over something to mean that it repeated infinitely, but we don't have that option in computers. So these numbers are not stored in decimal in our computer. They're stored in base 2, but there's lots of numbers that cannot be stored exactly in base 2. 0.1 is one of those, who knows how many different numbers, because it's not an even power of 2. I bet 0.25 could be stored in perfectly. I bet if we changed all these to 0.25s, we wouldn't get any rounding error because that's 1/4. I bet it would fit perfectly. All right, that's enough mathy math. I think we'll stop here. And I can't even think of any homework I want to assign because I don't think that we've done. We did a lot of theory, but we didn't do a lot of practice, right? We defined some constants. We did some prints. We did some size ofs. Oh, I guess I could make up some homework based on this. Homework. Write a program that creates a float variable and a double variable. Print out the value, the size of the float. Print out the size of the float using size of, and the size of the double. Same way. Put the value 1.23 into the float. You'll get an error message unless you put an F after it. So you're going to have to use 1.23F. And then put the value 4.56 into the double. You don't have to use the F to get it to work for the double. Now, I didn't specify names for the float and the double. You could just use F and D, right, for float and double, or call them Fred and Barney, or whatever you want. Then print the value of the float and the double. Remember to use %F. But to be more precise, let's use %.16F to display it out to 16 decimal places. And these notes show all of this stuff, right? We did all of that in class, so we ought to be good to go.
You say that, but
Yeah, you'll be able to do it. You'll be able to do it. And we'll come in early on Monday anyways. Knowing you and knowing me, we'll both be here. All right. Does that make sense? Yo, how you doing? Okay. And turn in the C file and the screenshot. Don't have to do screenshots during lectures.